Well, dear students, see in this lecture, I am going to discuss or explain the physical definition of entropy, dependency of entropy on various factors, and entropy change in reversible and irreversible process. But before going into the detail, first I am going to prove that why in irreversible process there is a creation of entropy. Means you can create the entropy during irreversible process. Means what I am trying to say, that I am going to explain here the Clausius inequality, that is entropy change in a reversible process is greater than 0, right? So for this I am considering this is a system, our system, and this is the surrounding, and you can assume this is the isolated system, right? Because this is in contact with this surrounding, and this surrounding we can treat as a hot reservoir, right? Hot reservoir. Let Q heat transferred from surrounding to system, right? Q heat is transferred from surrounding to system reversibly, right? Reversibly. Okay. So reversibly. So what is the entropy change for the system? As you know, entropy change for system reversible, and for system we can write system is gaining this Q heat, right? So it is positive delta Q by T. As we know that this our system is in contact with this hot reservoir, so temperature of both is same, right? And this is a reversible process, so this is system, this is surrounding, and all of you are knowing that T system is equal to, if your there is some processes going on in your system, then also you can write this T system is equal to T surrounding plus minus dt, and dt tends to 0. Dt tends to 0. See, this is always true for a reversible process, but this is not true for any irreversible process. Okay. So delta S system is equal to delta Q reversible for the system by T, and at the same time, what is the entropy change for this surrounding? The entropy change for this surrounding is how much heat lost by the surrounding? Q heat. So this is minus delta Q reversible by T. So this is equation 2. So we can write here what is the total energy, total entropy change. So delta S total is equal to delta S system plus delta S surrounding, right? So this is equal to delta Q by T reversible plus delta Q surrounding minus of delta Q reversible by T. So this is equal to 0. So you can say that in a reversible process, right? In a reversible process, the total entropy change means entropy change of system plus surrounding, entropy change of surrounding, this is equal to 0. And the best example of this is the phase change. Phase change, right? During phase change, whenever you are taking the change of phase from solid to liquid or liquid to vapor, total entropy change of system and surrounding, because this is a reversible process. A reversible process So for this, delta S total is always equal to 0. This is very, very important point, and means phase change means like H2O solid to H2O liquid. All of you are knowing that this phase change takes place at 1 bar pressure and 273.15 Kelvin. So and others, etc. Right? So for all phase changes, phase change processes, this entropy change of system plus surrounding, this is always equal to 0. Remember this. Not for system 0, not for surrounding only 0, but both system plus surrounding, this is always equal to 0. So see, in a reversible process, so first I have taken this is a reversible process, and our heading is irreversibility. Basically, in irreversible process, we are able to create the entropy, right? Reversible process. Reversible process. Right? So for reversible process, you can write that this is always true that delta S system is equal to the delta S surrounding, and you can write this in mod that delta S system reversible is always equal to delta S surrounding reversible, right? But the sign is opposite. So at any moment of time, if you take total entropy change, that for reversible process, that is equal to 0. And you know, if you remember our definition, what I have told you in the beginning of this chapter, that reversible process are always under equilibrium itself and equilibrium with the surrounding. And which type of this system I have taken here? This system is an representation of isolated system. This is isolated system, right? Because you have system and in this surrounding. So both we have considered as a whole, right? Because you know entropy is not defined only for system. The function is always, this is your compulsion that you should consider this surrounding to define entropy, as you have already gone through Kelvin statement and Clausius statement regarding the second law of thermodynamics, in which there is a hot reservoir that is mandatory there, and means you have to consider either surrounding as a hot reservoir or your system as a hot reservoir, or vice versa. You can exchange this. So system and surrounding both should be taken together to define entropy. But this is not the case with the energy, with the enthalpy, or with the Gibbs energy. This is one of the biggest constraints to explain any physical process or any chemical reaction in terms of entropy alone, right? So this is one of the reason why we are going for another thermodynamic function known as Gibbs energy to explain the spontaneous processes. So as you know that reversible processes are always under equilibrium, then they are not treated as a real process. Basically, they are not useful for us. The useful processes for us are only irreversible processes, and all natural processes are irreversible in nature, and all irreversible processes are spontaneous as well, right? So now see, in case of irreversible process, now second case I am taking irreversible process. irreversible process. So to estimate or to calculate the entropy change in an irreversible process, and to prove that Clausius inequality, that how this Q by T is greater than 0. So for this we have to design some process like this. See, suppose that our state 1 is this, and we are moving 1 to 2, 1 to 2, irreversible, irreversible. This is our point of concern. But to make it cyclic, we have to, or one have to make this closed cycle. So this I am taking from here to here, a reversible, right? Why we are taking our point of concern is only 1 to 2. We want to calculate the entropy change here, but our compulsion for us, because we want to see delta E is equal to 0. We want to make the system for which the energy change is 0, means energy should be conserved. So for this cyclic system, designing of cyclic system is important. See here also, this is both system and surrounding are in contact, so this is also represents a cyclic process, cyclic system, complete cycle. Similarly, if we want to calculate the entropy change in this irreversible process from 1 to 2, only this process is irreversible here. So we have to make certain cyclic system, so it is better to design from 2 to 1 reversible, right? Okay. And this from 2 to 1, if you consider entropy change of system and surrounding, then it is always equal to 0, and delta E is 0. So in a very simple way, you can calculate the entropy change for this, right? So this is very simple expression, we can prove this. Delta E 1 to 2 is equal to, we can write delta Q plus delta W, right? Delta W. And I'm considering this negative sign here, minus sign, as our standard notation is there, means I am taking here PdV, right? So delta W, so this is equal to, we can write delta Q plus minus P external dV, right? So this is equal to delta Q minus delta W. I am writing like this. This is our equation. See, this is minus PdV. So again, I am writing W in place of PdV, right? So I am considering this negative sign here. Don't think that I have changed the equation. Okay. Now, internal energy from 2 to 1. 2 to 1. So from 2 to 1, we can write delta Q minus delta W, and this we can write irreversible, and this we can write reversible. Any change or any problem? I think no. 1 to 2 is irreversible and 2 to 1 is reversible. What we can write here, that delta Q is equal to T delta S, T delta S minus delta W reversible, equation 2. See, I think this is clear to everybody that I am applying here thermodynamics first law. 1 to 2 is irreversible, 2 to 1 is reversible. So I have written here two equations by using thermodynamics first law, nothing else. So can we say that this delta E 1 to 2 is equal to delta E 2 to 1? This we can write. The answer is yes, we can write this. Because the initial state and final state is same for both. So whatsoever the internal energy is changing or energy is changing from moving 1 to 2, that is definitely the equal to the 2 to 1, but the sign is opposite. So that's why I have put it here mod, right? So from equation 1 and 2 we can write here that T delta S minus delta W reversible is equal to delta Q minus delta W irreversible, right? We can write this. So we can write here T delta S is equal to delta Q plus delta W reversible minus delta W irreversible, right? If you divide this equation, this is very important equation, and if you divide this equation with T, so now you have delta S is equal to delta Q by T plus 1 by T delta W reversible minus delta W irreversible. So see, this is a very important equation, equation 4. Now can you tell me that what is the relation between W reversible and W irreversible? Obviously W reversible is more than W irreversible. So if W reversible is more than W irreversible, so what will happen? What will happen to the delta S? What will happen to the delta S? Delta S now the delta S is greater than delta Q by T, because W reversible is more than W irreversible. So this term is positive, and temperature is always positive. So positive, this term is something positive. So this is added here in Q by T, and Q by T is the entropy with respect to the reversible change. So if you want to say delta S irreversible, so this is always greater than Q by T. So basically, this is the formula for calculation of entropy change in irreversible process, right? So this is delta S, this is greater than Q by T. This Q by T is equal to what? Entropy change of system in reversible process, right? So this term here, what we are using this in equation 4. So this delta, W reversible minus W irreversible, this difference is called here lost work. what I have used here the term lost work, right? So in this process, you can say, and what about reversible? If your this is a very general formula you can apply for reversible. When you apply this for reversible process, then what will happen? This when w reversible is equal to w irreversible is equal to w reversible, if you are taking the whole process what reversible, so this term is zero, so delta s reversible is equal to delta q by t. So basically this you can use to explain the reversible as well as irreversible process, both. So delta S irreversible, that is always greater than what Q by T, means the entropy change in reversible process, because in reversible process this term is zero. So this equation 4 you can use, equation 4 can be used to calculate the entropy change in reversible process as well. Reversible process. How? See, in if delta W irreversible is equal to delta W reversible, then this term is zero. So from equation 4, you can write delta S is equal to delta Q by T. So this in case of reversible process, we whatever the difference is coming here, how to interpret this delta W reversible minus delta W irreversible. See, this you can say that energy corresponding to this means in case of reversible process, more energy is required to do work on the surrounding by the system. So, and in case of irreversible, less work is done by the system to do the work on the surrounding. So, whatsoever the difference of these two works, that is known as the lost work, or you can say the energy lost. So, where this energy, transformed, basically this and lost energy, when you divide this with temperature, this becomes entropy. So you can say whatsoever the energy lost in the irreversible process, which is not converted into the work, that part of energy is now created as a entropy, now appears as entropy in irreversible process. So you can say that the energy which is corresponding to this difference of work which is lost, we can say that energy is appears as entropy in the irreversible process. That's why we say that entropy is created in irreversible process. That's why we say that the energy entropy is created in the irreversible process. So we can say that this part, very important conclusion we can write on the basis of this, that the W reversible minus W irreversible, this part we can say the unavailable energy for work, in irreversible process. And you know, this unavailable energy it appears as a entropy. It it appears as entropy in irreversible process, right? So this is the reason why sometimes we refer that the entropy is created in the irreversible process. Therefore, we can say that is entropy. Entropy is created in, in irreversible, or we can say natural, or you can say spontaneous processes. So in every irreversible process, there is a creation of entropy, and how much entropy is created, and this is the part of entropy created, right? And this term is referred as a lost work. Means whatsoever work is not obtained in irreversible process, that is known as what, lost work. And that lost work is not the actually lost, that will appears as an entropy in the irreversible process, right? That contributes in the entropy. Okay, say that the sink of entropy are impossible. Sink of entropy are impossible in nature. In nature. Okay, so we could write here that Clausius inequality delta Q by T is this. This contains is equal to 0, and irreversible by T, it is less than 0, right? So we can say that the entropy of an isolated system, of an isolated system never decreases, never decreases, right? Important word. These two are the important word here. Now see, again I am taking the same figure 1 to in state 1 to 2 irreversible, and 2 to 1, this is reversible. So this we can say path A, and this is path B. So A, the system is isolated, the system is isolated, right? And irreversibly, irreversibly, and changes from 1 to changes from 1 to. So we can write here that delta Q irreversible is equal to 0. We can write delta Q irreversible because this is isolated. System is isolated, right? See this this formula what I have derived here. This is a general formula. Now I am applying this condition that this is isolated and irreversible, right? So delta Q irreversible is equal to 0. So in this situation, and what is B here? And B is, what is B? The path B is, the system is brought, the system is brought into contact with a heat reservoir, reservoir and reversibly brought back two to 1, right? So this time path B is this is reversible. So what we can write here, Q irreversible is equal to 0. So delta Q by T is less than or equal to 0. This is equal to, we can write from 1 to 2, delta Q irreversible by T plus 2 to 1 delta Q reversible by T, and this equal to 0 we can write, equal to 0. So we can write here 2 to 1 delta Q reversible by T is equal to S1 minus S2, right? So this is equal to minus of delta S, and this is, right, less than or equal to 0. So, or you can say delta S is equal to S2 minus S1, and this is, right? So this you can write from here. And equality is for reversible and inequality for irreversible process. So this is what entropy change in reversible and irreversible process for what system, for system. So now see, this gives the direction of spontaneous change. This relation gives the direction of spontaneous change. If delta S is equal to, we can summarize here, for isolated system, isolated system. For isolated system, now you can write if delta S is greater than 0, then the process is spontaneous, irreversible, irreversible, right? If delta S is equal to 0, the process is reversible, that is at equilibrium. And if delta S is less than 0, then this is impossible. So these are the conclusions. But this is only true for what isolated system, not for other system. So this is the one of the constraint why we go for another thermodynamic function known as Gibbs energy, right? So now you can see from 1 to 2 this entropy change is independent of the path. So entropy change of system, this is independent of the path, but entropy change. So here we can write that the delta S of system, it is independent of path. Independent of path means delta S system reversible is equal to delta S system irreversible. Irreversible. But delta S surrounding depends on whether the process is reversible, whether the process is reversible or irreversible. Means if sometime it is given that for reversible process delta S of the system is this. So what is the delta S of the system for irreversible process? The answer is same. But the only difference we get that is for surrounding, delta S of surrounding. In case of irreversible process, delta S surrounding is not equal to the delta S system, and it is always greater than 0, right? So this is what we can conclude for entropy and its application to explain the spontaneous and non-spontaneous processes, right? Okay, now we will see that how to calculate the entropy change in different processes, right? Different systems. Now, see entropy, now we can define physically. Entropy is a measure of the disorder of the system. So, and we can make the definition that entropy is a measure of disorder of system, right? or randomness of the system, disorder of the system. Okay, so entropy is a measure of disorder of any system. This is the reason why if you compare, the entropy of gas is much larger than entropy of liquid, and entropy of liquid is more than the entropy of solid, right? Under the identical condition means if you take at the same temperature, so entropy of gas is always much larger than entropy of liquid and entropy of solid. This is the reason why in most of the reactions are physical processes where there is a transformation of phase, means from solid to liquid conversion is there. Entropy mainly derive that those processes, not much role of energy. Entropy is very important factor, right? So, and you see entropy of any system calculation. So I'm putting one note, important note here, that which is very important regarding the calculation of entropy. In all cases, we must find find a reversible path path to calculate the entropy of entropy of system, right? So we must devise the reversible path, right? So now see what is the formula for calculation of this. So I am giving you one master formula, and you can apply that formula to change that formula for different processes very easily. You can find. See, from thermodynamics first law we can write delta E is equal to delta Q plus delta W P. This is our fundamental equation. I am giving you the idea. By using this equation you can calculate the entropy. How? See, we can write from this equation delta Q is equal to delta E minus delta WP. This is equal to, you can write NCV delta T plus P gas dV, right? This is equation 2. I have considered reversible process. Reversible, right? So in reversible process, we have to take pressure of gas. This is variable here, pressure is variable, volume is variable, and temperature is also variable. So now if we divide this equation 2 by with T, so delta Q by T is equal to NCV delta T by T plus this P gas, we can write nRT by T and dV by V, right? So this T and T is cancelled here. So we can write here delta Q by T is equal to NCV delta T by T plus NR dV by V. Now every term you can integrate. Here, every term you can integrate. Now, this is also a state function. So, this equation is the master formula for the calculation of entropy. Now, see, all of you are knowing that delta S of system, reversible is equal to delta Q by T, right? So, if you are directly knowing that how much heat is transferred from the system and what is the temperature of the system, use this equation 4. Otherwise, if other variables are changing, then you can use this formula, right? So this formula and this formula, this is equal to this, right? So for this, if you have the heat change at given temperature, you can very easily calculate the entropy change. Now see, suppose that you have taken I am taking case 1. So I will show you that by changing in this formula, I will give you the entropy change for the system for different cases. First case, suppose that we are taking an ideal gas, expanding or compressing at constant temperature. Means under isothermal condition, if gas is expanding, then what is the entropy change? So entropy change of the system, delta S is equal to, you can write delta S system reversible is equal to, you have formula NCV122 delta dt by T plus NR dV by V. So T constant, so this term is 0. So you can write NR ln V2 by V. So this is the entropy change of system in isothermal expansion or compression of any ideal gas, right? Suppose that gas is expanding under isothermal condition, then you can use this formula. And if temperature is constant, then one more formula you can write here, that V2 by V1 is equal to P1 by P2. So NR ln P1 by P2, right? So delta S system reversible, this is equal to this. So under isothermal condition, you can calculate this entropy change of system by using this equation 1 and equation 2, right? Suppose that temperature is not constant. Means temperature is also changing, volume is changing, pressure is changing. Then what is the formula? So the entropy change in the expansion or compression of an ideal gas. This time isothermal, this condition I have removed, right? So what is the delta S of system? In this case, delta S of system reversible is equal to NCV ln T2 by T1 plus NR ln V2 by V1. This is equation 1. Or you can write NCP ln T2 by T1 plus NR ln T1 by T. This is equation 2, right? So these two equations you can use to calculate the entropy change of system in a reversible process. And you know, if the process is reversible, so what is the change of entropy change of surrounding? The same magnitude with opposite sign, right? So in this way, you can calculate the entropy change of surrounding as well, right? So now see third case. Suppose that you are taking, entropy change where there is no change in volume, isochoric condition is there. So the, this part under isochoric condition only heating or cooling is there. So only this term is there. Only this term is there. This term is not applicable there. So under isochoric condition means heating or cooling or some heat change, you can use this form. So under isochoric condition, entropy change of system entropy change of system in heating or cooling. Heating or cooling. Right? So and or cooling. Heating and or cooling. So in this situation, the entropy change of system reversible is equal to NCV dt by t. You can use this equation, or NCP dt by t, right? Under constant pressure condition and isochoric condition, if it is given, then you can use this formula, right? Now see, mixing of two gases, you can use mixing of two gases, mixing of two gases, right? Mixing of two gases. See how to calculate at constant T and P. This time temperature and pressure is constant, right? So suppose that there is a mixing of two or more gases, if T and P constant. See, suppose that N A moles of gas A gas, and volume is VA and temperature is T, plus NB moles of A, or NB moles of B, NB moles of B gas is taken, and volume of this is VB and temperature is T. After mixing, the total moles becomes Na plus Nb, right? And A plus B gas, and now the volume becomes Va plus Vb and temperature is T, right? So how to calculate the entropy change? Now see, what is the see, I am taking gas A, and gas A in the mixture. So gas A, what is the entropy change for this gas A? So initial state of the gas A is this, and this is the final state of gas A and B both. So for gas A, entropy change from this to this, right? See, this is initial state and this is final state. Initial state is different for A and B, but final state is same. So for gas A, delta SA is equal to, how many moles of A are there? Na R ln VA plus VB. This is the final volume, VA plus VB by VA. Can we write this or not? This is the final state for the gas A, and this is the initial state for gas A. So the entropy change for gas A is equal to NRALN V2 by V1, and P are constant. So this is the entropy change for gas A. This you can write minus of Na minus of Na R ln VA by VA plus VB, right? And this is called VA by VA plus VB. This is directly proportional to the mole fraction of A. Means you can write this is equal to Na by Na plus Nb, right? This you can very easily write because T and P are constant. So if T and P are constant in this situation, you can write volume fraction is directly proportional to the mole fraction, right? So you can write here minus Na R ln mole fraction of AXA. Clear to everybody? Okay, I think there is no problem. This is equation 1. Now, what is the entropy change for gas B? Entropy change for gas B. So, this is the initial state for gas B, and this is the final state for gas B. So, we can write here similar manner NB R ln XB. Same manner you can write. And what is the delta S of mixing? So delta S of mixing is equal to delta S of A plus delta S of B. So this is equal to minus NAR ln XA minus NBR ln XB, right? So you can write here minus of R NA ln XA plus NB ln XB, right? Or you can write here, minus of N into R XA ln XA plus XB ln XB, right? So this is the delta S of mixing. By using this equation, you can calculate the delta S of mixing, where this N is equal to Na plus Nb, right? So see here, if we multiply and divide this equation with N, where N is Na plus Nb, So multiplication here n, and in the division this will by n total and this by n total. So this is mole fraction. So this is the simple formula, and you know what formula we are using to calculate this delta S of mixing. This simple formula we are going to use. So by using this formula, you can calculate the delta S of mixing, right? Similarly, next case, fifth case, we can take entropy change in phase transition. Entropy change in phase transition. So all of you are knowing that phase transition, suppose that a solid to a liquid. So this is T is constant, P is constant. So if T is constant, P is constant, so you can write here that delta Q, whatsoever the heat change, and it is a reversible. Although phase change could be irreversible, right? But we are considering here a reversible phase change. So this is equal to, we can write delta H fusion for this at constant T and P. We can write this. So what is the entropy change here? The entropy change is delta S is equal to S A of liquid minus S A of solid. This is equal to delta Q by T, and this is equal to delta H fusion by T. So in the phase transition, you can calculate the entropy change by using this formula, right? Now, if a liquid to a vapor is given, so in this case the entropy change delta S is equal to S a vapor minus S a liquid is equal to delta H vaporization by T, right? Okay, so since we have the total heat change, what heat is changing here, so we can use this heat change at given temperature to calculate the entropy change in the phase transition, right? So these are the different cases which you can use to calculate the entropy change, right? Now, see, this is irreversible phase change at constant temperature and pressure. This is a very special case. You won't find very easily this type of process, but we cannot say that such type of process are not possible. See, H2O liquid minus 10 degrees Celsius and 1 bar. So this, if you are able to decrease the temperature of water liquid without freezing this, so such type of liquid is known as super cooled liquid, right? And you know, this type of process is possible to achieve this by controlling the entropy of the system. And if you you can devise this type of system, but remember, if a very small turbulence is there, a very small disturbance is there, immediately whole water will freeze out immediately. So this process is irreversible and spontaneous, right? And definitely when this process will happen, this is very fast. This is very, very fast. But we do not have any formula to directly calculate this entropy change in this step. So we have to design the reversible path for this. And definitely, you know, this is state function, so there is no problem to calculate the entropy change of system. In the beginning of this, I have already told you that the entropy change of system is always equal, whether it is reversible or irreversible. No problem. So don't worry. So you just devise the path, reversible path for this. So see how to devise the reversible path for this. So you can write here H2O liquid at minus 10 degrees Celsius and 1 bar. First, this will convert into H2O liquid at 0 degrees Celsius and 1 bar, right? And this time, whatsoever the heat change delta Q reversible, this is equal to, you can write Cp of H2O liquid dt. And Cp delta T, all of you are knowing. And now this will transformed into the H2O solid at 0 degrees Celsius and 1 bar. And this time delta Q reversible is equal to this solid to liquid, so we can take here minus of delta H fusion, right? Because this is liquid to solid, and after that we can reach to the final state H2O solid minus 10 degrees Celsius and 1 bar. So this time delta Q reversible is equal to Cp of H2O solid dt. So all these paths are reversible since initial and final states are same. So the entropy change will be the same, right? No problem. For the system, not for the surrounding, right? So this is the path design. We have designed the path. Now we can calculate. We can use the formula for this. So delta S is equal to, we can write delta S is equal to delta S, this is what? Delta S1, this is delta S2, this is delta S3. So delta S1 plus delta S2 plus delta S3, right? So we can write here minus 10 degrees Celsius. You have to convert this in the to the Kelvin when you are using the formula. And T fusion, this step, Cp of H2O liquid, right? And dt by T, right? Plus minus of delta H fusion by this 273.15 Kelvin. This is T fusion is basically 273.15 Kelvin plus T fusion to minus 10 degrees Celsius. So this is Cp of H2O solid dt by T. So by using this equation, you can calculate the total entropy change in this process, right? And we are assuming here that the Cp are the independent of temperature. So in this way, you can calculate the entropy change for such irreversible phase transition, right?